Good afternoon, everyone. I wanted more attendance, but let me start. Am I audible, guys?
Yes, sir.
Thank you. Right. So I'll revisit few of the steps in DES. As I mentioned in the last session, that some of the figures are pending here. So this is that figure that I was searching in the last session. I could not pull out this figure. So this is the bird eye view of DES. So where do you need, what exactly is the number of bits are getting transferred, and all these things are mentioned. And these are the basic steps which are involved in DES. So I'll just quickly go through this diagram. So initial permutation, changing the positions of bits, 64 bits. That is the first step. Then you'll have 16 rounds. And after 16 rounds, you have a 32-bit swap. So first of all, the text, you have to divide it into two halves, L part and left part and right part. And then at the end of 16 rounds, you have a 32-bit swap. That means, again, whatever you are getting as a left part here, that should be swapped with the right part and vice versa. And then whatever the permutation you have got here, that has to be reversed at the as a last step. Okay, so this is a complete encryption, DES encryption, that is data encryption, standard encryption. Now at each step you are working on 64-bit data, or each round you are working on 64-bit data. Then at each round you'll need a separate key. For that you'll have a key generation algorithm. Okay, now in this key generation algorithm, the keys are getting compressed a couple of times. So first you are getting a 64-bit key, then after applying some combination, changing the bits of combination, you're selecting only 56 out of those 64 keys. What I'm going to do is I'm going to give you the example. Okay, so we'll see the example how exactly what data is getting transferred after each step. So you'll have an idea of what's happening. Then you know that we have discussed that we'll have a circular shift, either 1 bit or 2 bit depending on the rounds. After that circular shift, we again will compress that key to prepare a 48-bit key, okay, which will go into the round. Okay, now what is happening in the round is detailed in this diagram. So as you know, every section is divided, every plain text is divided into two halves, L part and right part. The feastal function that we have seen has 4 steps, basic steps. First one is the expansion. Why do we need expansion table? Because a right part is a 32-bit part. Okay, the size of the right part is 32-bit, but the key which is coming here is a 48-bit key. So if we want to work on these two data, this 32-bit data has to be expanded to 48-bit. So that's why we should apply a expansion table, okay, E table. That also we have seen. I'll revisit it again. So first step will expand 32-bit data into 48-bit. The second step is simple XOR operation. And then whatever the output you have, 48-bit, again the output of this feastal function has to be a 32-bit data because it has to be XORed with the left part. So again, to prepare a 32-bit data, you'll have to reduce this 48-bit into 32-bit. So for that, we have seen substitute box, that is S box operation. And then the last one, changing the bits. Again, some permutation combination we have to use for changing the bits. Okay. Now, if you have noticed, every step is increasing the complexity of the encryption. Okay, we are trying to increase the complexity, which is introduced by Feastel, the scientist Feastel. Okay, so this is a actual encryption part. What is happening at uh, the key generation part? Key generation part, as you are getting a 56-bit key after permutation combination. So first one, permitted choice one, you are reducing. This is a compression step. From 64-bit key, you are generating a 56-bit. Now, once you get the 56-bit key, again, you are dividing it to two halves. One is this one and other one is this one. Both the halves will be shifted or circular shift twice. Okay, so one is here and other one is here. And then again, you have to reduce it because this is a 56-bit data and it has to be reduced to 48-bit data. That's why again, another table you have to refer. Okay, and then this you'll have to do it in a loop to prepare how many keys? 16 keys, because for each round you'll have to provide a separate key. Okay, so that has to be performed in a for loop. So this is the initial permutation, as I have explained this earlier. So let's say first bit is going at 40th location, second bit is going at 8th location, and so on. So this is the changing of bits, and you have to follow this hard-coded table. And this is the last step of DES, where you have to perform inverse initial permutation. Now, inverse initial permutation means what? You have to get the original bits back on their original positions. So if you have noticed here, if first bit is going to 48th bit in the new position, so at the end, if you want to reverse or inverse this step, 40th bit again you have to bring back to the first position. Okay, so if you are copying first bit at 40th, to inverse 40th bit again, you have to copy back to first position. Similarly, second one, if the second one is going to 8th location, so 8th bit has to be brought back to the second location, and so on. Okay, so for the inverse combination, you have to follow this matrix. Okay, so this is the first step, and let me give you the example here. Okay, so let us say your message is this one. Original message M is 0 1 2 3 and so on, A B C D E F. This is the original message. Okay, so when you convert it into a 64-bit block, this is a 16 character format. Okay, so this is a first block of the DS ciphertext, and this will be considered as a plain text. So what you do is you convert it into a binary. Okay, this is a 64-bit data. First thing first, you have to divide it into two halves. One is the left part, so first 32-bit, and the right part, remaining 32 bits. Okay, so that is the first step. And second step, you have to get the key also, key of 64-bit data. Again, we are getting 16 characters, so as to form 16. This is a now random data we are generating. It is not fixed that you have to get this key as it is. Okay, it depends on you what kind of key you want to use. Okay, so this is a 64-bit data again. Let me take you to this part. Okay, we were looking at uh, the plain text. When you apply initial permutation IP, what should happen? Okay, so IP says a 58 as an entry of first data in the matrix. That means what? The original message M. Okay, you have to find the 58 bit in the original message, and that 58 bit you have to bring it to the first location. So that is the meaning of this matrix. Okay, similarly, the first bit is copied at this location. So this is the actual 48th location. So what you have to do is you have to copy the first bit, that is 0th bit, at the 40th location in the new permitted combination. Okay, so this is a simple step applying the initial permutation. Now here, are there any questions, some queries with this here? Okay, after the first step, next step is the key generation part. Okay, now what happens is how to create a 16 sub keys, okay, which are 48 bit long. Okay, so key generation algorithm is very, again, the simple thing. So first one is to apply permuted choice one table. Okay, what is that table? It reduces a 64-bit key into a 56-bit key. So these are all 56 entries. Let us count it. 1, 2, 3, 4, 5, 6, 7, 8 into 1, 2, 3, 4, 5, 6, 7. So 7, 8, 56 entries are there. So obviously, if you apply this same logic, whatever we have applied to IP, the same logic, that means 57th bit is coming at first location, 49th bit is coming at second location, and so on. So I guess some of the bits are excluded here. Okay, so I think 13 is not there. So similarly, some bits are not considered in this table. So that means reduction of it will be reduced from 64 bit to 56 bit. So once the 60, so this is a 64 bit key, and this is a, after applying PC1, that is permitted choice one table, this key will be prepared. This is a 56 bit key. What you have to do is you have to divide it, this key, into two halves. One is C part and other one is D part. We cannot name this as L0 and R0 because L0 and R0 we are already considering it for the plain text. So that's why we are just denoting it with C and D, C0 and D0. So obviously this 56-bit key, 28 and 28 bits are mentioned over here. Okay. Now, as you know, for each iteration, what we are doing is we are using a circular shift, left shift. Okay. So what you can do is once you get C0 and D0, you directly apply number of shifts to both the parts. So after applying one shift left to both the parts, what will happen is, so this is a C0, D0, C1, D1 will be, it is exactly a 1-bit shift left circular. Okay, if you can think of this, let's not, write it on a paper. Like you can calculate on a paper bit later, but these are the number of shifts that are applied depending on the iteration number. Okay, because for each round, you'll need a separate key, and there are 16 rounds, so we have to create 16 different keys, and 16 different keys will be prepared like this. Okay, so this is how we are preparing all the keys here. And when you combine C0 and D0 again, you'll get all the keys, K1, K2, and so on. Okay. Once the keys are prepared, again, what is the length of this key? Let us consider this as key 16. What is the total length of this key? Is anyone?
56.
This is a 56-bit key because you have divided a 56-bit key into two halves. This is a 56-bit key, right? So this 56-bit key, again, you will have to reduce it to 48-bit key, okay, by applying PC2, permitted choice 2 table. Again, you'll have to reduce it to 48-bit key by applying this table, PC2 table. Okay, what I'll do is I'll share this document with you, the example document. You can directly implement the program from this document. Okay, so once you apply this table, again, 14th location bit is copied at first location and so on. So the logic is same. The only thing is the matrix is different at various stages. So IP is different, initial permutation is different, which what it does, it rearranges 64 bits in itself. PC1, it is the same thing, similar thing, but with reduce approach, where 64-bit is reduced to 56-bit key. When you are applying PC2, 56 again will be reduced to 48. Okay, and once you are getting 48-bit keys, okay, by applying this logic, these are the all keys for all the 16 rounds. Okay, so these are all the 48-bit keys after applying PC2. Okay, any doubts here? How the keys, sub keys are generated?
Sir, I did not understand how it happened. Could you explain it again?
Okay. See, I'm not working on the values. Okay. Let's say, let us say this is a 64-bit key. Okay. The user has entered. Okay. There are two inputs to this program. One is the data, actual 64-bit data. Okay. That is this data, right? And the other one is key. Okay. So once the key is 64-bit key is generated, what you have to do is you have to apply, you have to reduce it to 56-bit. Okay, by applying some reduction logic. What is that reduction logic? Is this one, this table, PC1 table. That means what? Let us count the 57th bit. Let us count it from the last one. 64. This is a 64th bit. 63, 62, 61, 60, 59, 58, 57. 57th bit is 1. Okay, so 57th bit is 1. So that means this one is getting copied at the first location. Okay, so that is this one. So if you apply, this is the input and this is the output. So if you apply this table on this input, you will get this as an output. So 57th bit you are copying at first location. So what is the second bit? 49th. So you'll have to find 49th bit. You'll have to get the 49th bit from this data and you'll have to copy it to the second location. Similarly, third location, 41st bit, you have to get the 41st bit from this data and you'll have to copy at the third location and so on. Is this
So sir, we are just creating that permutation using this table. Like
yes,
whichever is the first, then uska bit we'll be copying it.
correct,
That.
correct.
Okay, sir.
So it is the similar, yeah, if you have if you can see this yellow figure, it is the same concept. So as first bit is getting copied at 40th location, second bit is getting copied at 8th location, and so on. Similarly, 58th bit is getting copied at first location, and so on. So this logic you have to apply to whatever the data you have got. Okay, so only the thing is, this is a PC1. You are applying this logic to key generation part, and some of the bits are not considered. If you have noticed, this is a 64-bit key and this is a reduced key. So this is a 56-bit key. So 8 bits are discarded directly. So I think the 13 is not seen. Can you find out 13 in this table? I guess it's not there. It's there. Okay, sorry. You'll have to find out which bits are discarded. You can find it out later. But this is the logic. You have to reduce it from 64 to 56. Okay, so this is what first step. The second step is to divide it into two halves. This 56-bit key, we have to divide it into two halves, C0 and D0. So now this is a C0 and D0. What the algorithm says that once you have divided it into two halves, you have to apply the left shift logic, circular left shift logic to both the parts. Okay, so and what is that? How many bits you have to use as per the round? Let's say you are creating a key for the first round. In the first round, C0 and D0 will be shifted left by one position. These are the number of shifts per round. Okay, so let us try to see, yeah, this one. So if for the C0, if you are shifting this data circular shift by 1, what you are getting, you'll get this data. So this one is going at the right end, so there will be 5 ones here. Yeah, there will be 5 ones here, and instead of 4 ones here, there are 3 ones, and every bit is getting shifted to 1. Okay, so this is the left shift operation on left part. On the same thing we'll have to apply on the right part. So D is the right part. Again, you have see this one is coming at one location here, this 0 is going at the end, and so on. Okay, so this is the first round key. If you combine C1 and D1, this is the first round key. Okay, and similarly, I'm sorry, this logic you'll have to apply for all the keys, C2, D2, C3, D3, and so on. For each round, you are getting this as an input for the next round. For the next round, this will be the input, and so on. Any doubts here? And when you combine C1 and D1, it will become a key. Now, once that shift operation is done, what you have to do is that shift operation is not reducing the data. What is the total data you have? Total data at each round, 28 plus 28, that is 56 bit. Okay, the actual key has to be a 48 bit key. So it has to be reduced again. Okay, it has to be reduced again. So again, for that, you'll have to apply some permuted choice table. okay, which is helping you to reduce. Again, some of the bits are discarded from this 56 bit. Okay, so this is the half part of that matrix. Okay, the logic is same. Again, 14th bit. Let's say, can we consider the C1 D1 from the first? Say C1 D1 for what is the 14th bit? 1 2 3 4 5 6 7 8 9 10 11 12 13. 14th bit is 0. Okay, so K1 should have first bit as 0. Let us try to find out. Okay, so what does it say? When you combine C0 and D0, whatever the data you'll get, from that data, 14th bit should be coming at the first location. Okay, so when you apply this logic, we just have found out the 14th bit from C0 D0, C1 D1 is 0. So the C1 D1 is given here, and 14th bit is 0. So the first bit is 0 here. Okay, so when you apply this permitted choice table on each C1 D1, C2 D2, and so on, you are getting these keys for each round. Throw some doubts, please. See, it is, yeah. See, what happens is when you see the example, it becomes, bit difficult. But when you just go back to the this logic or algorithm, you just have to, think of how it is, executed. Okay, when you say how it is executed, you need some data to understand. Okay, and when you see such number of bits, then you get confused. But if you take one at a time, you just try to understand how C1 D1 is getting converted from C0 D0. Just take one example, you'll understand that logic. Okay, and then the same logic, you just have to shift these number of bits. For some rounds, it is shifted by 1 position. For some round, it is shifted by 2 positions. So let us try to see on the third round, it is shifted by 2 positions. So that means C2 has to be shifted by 2 positions. So these 2 ones are going at the end at C3. So when these 2 ones are going at the end, obviously these zeros are coming here. So these 4 zeros are coming here. So at this step, it is not 1 bit shift, but it is 2 bit shift. When you apply PC2, it will reduce the total length. This is a 56 bit length. You'll have to get the 48 bit length. So each pair has 56 bit. When you apply PC2, it creates a 48 bit key. Okay, so these are the keys which are getting generated. So this is a sub key generation algorithm. Okay, now we have already seen this, that is a 64-bit data has to be applied with the initial permutation, that is changing of the locations. Now remember here, we cannot reduce the 64-bit data with a PC1 PC2 like PC1 PC2, because otherwise we will lose the original data. We don't want to lose the original data. That's why we are not changing the number of bits. Okay, the number of bits will be same throughout the throughout this process. This is the encryption process. At the start, you'll have 64-bit data. Whichever step you apply, you have to have a 64-bit data only. You can play with number of small number of bits here, number of keys. That is just to increase the complexity. Okay, but here you have to work with the 64-bit data because we don't want to lose any original plain text. Okay, so once we apply the IP, that is the first step, you get this as an output. Okay, then you'll have to divide it into two halves, L0 and R0. So at the first step, whatever you are getting here, it has to be divided into two halves, L0 and R0. Now what you have to do here for left part and right part is this one. Okay, so you'll have to apply this function f, feastal function f. Okay, feastal function f. So whatever the output of this feastal function, that has to be XORed with left part. Okay, so that is given over here. So how do you calculate left part and right part? So for the next round, okay, for the next round, you are getting the previous right part, previous round's right part. So for the next round, you are getting the previous right part as it is. So Li has to be equal to Ri minus 1 as it is. But Ri cannot be same as Li minus 1. It has to be encrypted. Okay, how it is encrypted? Li minus 1 XOR with f of Ri minus 1. So you are applying feastal function on right part of previous round. Okay, and that output you are XORing with left part. So this is exactly written in a mathematical formula here. Right part of the next round is equal to the previous left part XORed with the function, feastal function on what? There are two inputs for the feastal function, the right part and the right part of previous round, or n minus 1, and the current key. Okay, so the current key and the right part are the two inputs for this function. So that is what it is mentioned in the. So when you see the algorithm, these will be the mathematical terms you will be reading out in the books. So you should not be getting confused with that. It's just a mathematical representation of what we have seen in this diagram. Any doubts here? Okay, now let us try to apply feastal function f on the right part. Okay, now feastal function starts with an expansion table. What is the job of expansion table? To convert this 32-bit data into 48-bit data. Okay, for that, what we have to do is, if we copy some of the bits, more number of times, let's say this bit, we are copying it at two locations, one at this location and other one is at this location. So obviously 32-bit data will be converted into some more bits. Okay, and this step, expansion step, is going to be converting this 32-bit input into 48-bit input. Okay, and this is the expansion table. Okay, so expansion table is very simple. See, first location, of 48-bit is getting copied from the 32nd location. So this 32nd bit, okay, is getting copied at 32nd location also, this location also, and the first location of the new data also. Okay, then 1, 2, 3 are getting copied as it is, 1, 2, 3. Okay, but the fourth location is getting copied at two locations. So this one fourth and this one fourth. But the fifth is getting copied at two location again, fifth at this one and this one. So this one and this one. Okay, so this is just a evaluation of how the bits are getting expanded. Okay, this is the expansion table. Again, you while coding this table, you'll have to hard code in the program. Okay, and then you'll have to just find out the value. So input will be this data. Okay, what you'll have to do is array. Let's say this is a array. Okay, a of 32. You're copying it at first location as well as at this location. Okay, ARR of let's say a of 1, you are copying at new location. Let's say this is b location, this is b array, b of second. Okay, and so on. So this will be a very simple loop to create a 48-bit from the 32-bit. So this is the first step of expansion. The second step is to XOR the key which you are getting in that round. Okay, you have already got the key. Okay, so this is the expanded data from the R0. This is a 32-bit data. This is a 48-bit data. What you'll have to do is you'll have to XOR. The next step in the Feastal function is to XOR key 1 with the expanded data. Okay, so when you apply the key, this data will be XORed with the expansion. So you can directly see that 0 XOR 0 is 0, 0 XOR 1 is 1, and so on. 0 XOR 1 is 1, and so on. So you can apply this XOR operation. So this is the output of the second step in the Feastal function. Okay, now what is the third step in the Feastal functions? Third step is the S box. Now the problem here is we have the 48-bit data. Okay, but output of the Feastal function has to be a 32-bit. Okay, that's why we have to reduce it again, compress this data into 32-bit data. Okay, and for that we will have to use S boxes. Now last time we have seen that how to use S boxes. From the 6-bit, how to convert into 4 bits. Okay, so if you remember, the first and last bit defines the column, and middle 4 bits will define the the vice versa. First and last bit are defining the rows of X boxes, and the middle 4 bits are defining the number of columns. Okay, so you have 4 rows and 16 columns in the one S box. Okay, so for example, if you have 101110, what you'll have to do is take the first and last bit, and that will constitute which row number you are referring to. So in this case, 10 will refer to the third row. Okay, and the middle 4 bits, that from the bit number 2 to bit number 5, it will constitute 0, 1, 1, 1. So you have to select that particular column. Okay, now this data of S1 is fixed. What you'll have to do is you'll have to get that value. You got the row number, you got the column number, you get that value and convert that digit into a binary value. In this case, it is 11, so 101. Any doubt here? Sorry, someone was. The job of this step is to reduce the 48-bit data into 32-bit data. Okay, for that, what you have to do is this 48-bit data, you have to divide it into eight groups of 6 bits each. Okay, so there are 8 inputs for 8 S boxes. 6 bits input for each S box. Each S box will produce a 4-bit output. Okay, so obviously when you combine these all 8 groups with 4 bits, you are preparing a 32-bit output. And how you are getting 4 bits from S boxes? This is the logic. And S boxes are fixed. This data you'll have to hard code. S1, S2, S3, S4, S5, S6, S7, and S8. These are fixed. Any doubt, guys? Am I audible?
Yes, sir.
So if we try to see the example, we are preparing the boxes here, 8 boxes, B1, B2, B3, and so on. These are the 6 bits boxes. Okay, and you are applying the S1 table on box B1, S2 table on box B2. Okay, so this is what it is happening. B1, S1 box you have to apply on B1. This is B2, S2 box you have to apply on B2, and so on. Once you apply that, you will be preparing the 4 bits. This is the example. That example we have just seen here. Okay. Similarly, you have to repeat this for all the blocks, B1, B2, B3 till B8. And S1, remember S1 you can't apply for all the boxes. S1 has to be applied on first block, that is B1. S2 you'll have to apply on the second block, that is B1. So just like this, S1 on B1, S2 on B2, S3 on B3, and so on. Okay, now the last step of the function, Feastel function, is the P box, that is the permutation. All these 32 bits data, whatever you have got from the previous step, that is S box, you have to again change the positions. Okay, so 16th bit is coming at first location, 7th bit is coming at second location, 20th bit is coming at third location, and so on. So again, this is hard coded, this is fixed. Okay. As a last part, what you have to do is whatever the Feastel function you have got, that has to be XORed with the left part. Okay, that we have seen. Yeah, this one. So this one is done. Feastel function on right part and the key. Okay, whatever you are getting, you'll get a right part of the next round. Okay, so that you'll have to copy it and in the next round. Okay, so that is the swapping which is needed. Okay, and at the end, the one swap operation is needed. The L6 and L16 and R16 has to be swiped. Okay, so I'll have to go back to the one of the this one. So last 32-bit swap is needed. So after all the rounds, whatever the output you are getting as a left part and right part, that has to be swapped. Okay, And the last step is to apply inverse initial permutation. What is that inverse initial permutation? It is exactly reverse or inverse thing of IP, which is the first step of DES. Okay. So, and once you apply the IP inverse table, whatever you are getting is the encrypted text of 64-bit block. Whatever you have started with 0, 1, 2, 3, 4, 5, whatever. This is the original data. The cipher text is this one. Okay. Now, this is what the explanation of DES, the complete DES. Okay. Now, let me tell you this thing. When the FEASTIL have applied for, that NSA asked for the multiple algorithms, FEASTIL has submitted this as a DS algorithm. Okay. And he submitted all these steps. He told the whole world that this is how the encryption will happen. Okay. But still, no one could find or no one could break the DES for 23 odd years. So it was broken. DES was broken in around 96, 97. So can you tell me the reason behind this? Any idea? Can you think of something? So let me put this screen for you. The answer lies, in this diagram. When the every step is known to the hacker, why the hacker doesn't, could not, there were many hackers trying to break the DES, but they could not break the DES for 23 years.
Is it because of the permutation steps? Because even though you have only 1 or 0 as your bits, because you have 2 to the power 32 sort of positions where you can place them, the permutation is where you will get stuck.
See, actually, these permutations also are known to the hacker. Which bit is going where? This is also known to hacker. So if he wants to bring those bits back to their original position, they know that which bit has to be brought back to the original location. And every step is known. How many bits are getting shifted? Which bits are discarded? Which S box? What is that operation which is happening after expansion? Everything is known to the hackers. Okay, I'll give you the hint. Answer lies in this slide. Bit closer. See, you should be asking the question from where these values are coming. Why the S box, S1, is defined like this. Why there is a 14 here, why there is a 4 here, why there is a 13 here. Why these values, from where these values are coming. That is not given by feast-fill function. I'm sorry, feast-fill guide. Okay, so no one could find out how these S boxes are generated. Feast-fill have given these S boxes that you have to apply this logic, but he did not tell anyone how he came to these values for the encryption and decryption. Okay, that this is the very difficult part of DES, to apply these S boxes, and this is the only strongest point of DES. The weakest point was these permutation combinations. Okay, which bit is going where? When you're telling someone that this bit is going here and this bit is going there, you know, this is a weakness of your algorithm, because if you're telling that you are going there and you are coming here, there's no point in doing that step. So this was the weakness of DES, and with this weakness, hackers could manage to find out how the S boxes were defined. Okay, but still it took 23 years for the hackers to break this logic. Okay, but anyway, your job is to perform this task, okay, as a program. If you have any doubts, we can discuss it during the what you can say practical sessions. If you have still not understood, I can conduct another session for you. But again, it will be repeated session. I have recorded the last session as well, and this session as well. So if you want, you can refer